So today we are going to be looking at Gibbs Free Energy. And so this is kind of the second half of chapter 12. So chapter 12 basically had two parts. We did the first part yesterday, talked all about that entropy stuff, all of that disorganized energy distribution kind of knowledge. And now we're going to kind of put it together with the concept of Gibbs Free Energy. And again, we realized yesterday that as far as entropy was concerned, yes, we could predict spontaneity using entropy, but only if we had a means of determining the entropy change for the universe. And that was where we kind of ran into difficulties, because it was very easy to determine the entropy of the system, but it was not so easy to determine the entropy of the surroundings. We had some ways that we could do it, but there were always limitations. And so what it comes down to for us is there a means, is there a way that we can determine the spontaneity of a system by merely looking at the system and not having to worry at all about the surroundings? And that's where Gibbs Free Energy comes in, because we know that things that are exothermic tend to also be spontaneous. And we also know that things that tend to increase in entropy of the system also tend to be spontaneous. But we also know that there are exceptions to each of those rules. There are exothermic reactions that are not spontaneous. There are entropy changes that are positive that are not spontaneous. And we've got the reverse things happening as well. Formation of a precipitate doesn't favor entropy, but we know it happens in certain circumstances. Endothermic reactions happen all the time that are spontaneous. Saw an example of one yesterday. So what we really need is a system that will give us the correct answer every time without exceptions. And that's where Gibbs Free Energy is going to come in. Because what it's going to allow us to do is it's going to allow us to tie together those concepts of enthalpy, entropy, and temperature and cover them merely from the position of the system and ignoring the surroundings, which is going to make our lives a heck of a lot easier. So the Gibbs Free Energy equation says that the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy. And we just got to remind ourselves again that with these thermodynamic equations, we are talking about temperatures in Kelvin. So when we did this in thermochemistry, didn't matter if it was Kelvin or Celsius, because changes in temperature, which were what we were looking at, and the change in temperature is the same on the Celsius and the Kelvin scale. But when we're looking at just absolute temperature and not change in temperature, we've got to use that absolute scale. We've got to use the Kelvin scale, because that is the only one that directly relates temperature and energy to each other. If we did see Fahrenheit, we would have to either have a specific heat that was Fahrenheit as well, or we would have to make the appropriate conversions to Celsius or Kelvin to do that. Now, there is an absolute scale for Fahrenheit. It's not Fahrenheit, obviously. It's called the Rankine scale. So there is a Fahrenheit equivalent to Kelvin, but obviously we don't use that because we follow the SI system. The SI system uses Celsius and Kelvin, so that's what we use as well. That keeps us with the international standard. But there is, so if you look, at certain kind of tech manuals or things like that, you will see that there is this other scale, degrees R, and that's basically the Fahrenheit equivalent of an absolute scale. So there is one that exists. It's just that's not our purview. That's not our perspective. So this equation covers us for basically any kinds of conditions that we might encounter if we are at standard conditions. And remember, standard conditions are 1 bar of pressure, 25 degrees Celsius, 1 molar concentration. Under those conditions, we can put the little degree symbols back on everything. And that would indicate that we are at standard conditions, and we could get a standard Gibbs free energy change. So how we need to look at delta G is that we're looking at kind of a totality of energy, all the different types of energy, all woven into this one calculation. And so from this perspective, now we can evaluate delta G and look at whether or not energy is required or whether or not some energy is being given off by a system as it proceeds. So if delta G is positive, that means that the net energy flow, the total energy flow, is positive. It is coming into the system. And energy flow into the system is going to mark a non-spontaneous process, because that means that we have to continually provide the reaction energy in order for it to run. And that completely negates our definition of spontaneity. Spontaneity says that the reaction can run on its own without our interference. If we have to continually supply it with heat, then it's not running on its own. If delta G is negative, that means that the reaction is releasing net energy. This would be a spontaneous process, meaning it would run on its own. We might need to provide it a little bit of activation energy to get the whole party started. But once that activation energy was present, the reaction itself would generate enough energy to supply the activation energy for the rest of the reaction plus extra output. And if delta G is equal to 0, then what we are seeing is no net energy change. If there is no net energy change, that means that we've got a reversible reaction going on. We've got a system at equilibrium. Both reactions are running equal and opposite to each other at the same time. Yes, but our interpretation would be different, because with delta H, we're talking about heat energy specifically, whereas with delta G, we are talking about overall total energy. And so there is a difference in terms of the interpretation, because we know that if something is exothermic, that doesn't necessarily mean it is spontaneous. Whereas if we have a reaction that is exergonic, which is the term we use for spontaneous reactions, then that's exactly what it is. It's spontaneous. So the terminology here, you're not going to need to know this. but I said it, so I'm going to so instead of exothermic and endothermic, the terms are exergonic and endergonic. Now, again, these are not terms that are in your textbook. You don't need to know them, but I said them. I don't want you to try to figure out how to spell them, so I'm giving them to you here. Again, you're not going to see it. It's not important information to you, but those are the appropriate terms when we look at free energy directionality. But the interpretation is kind of the same. Negative is good, positive is bad, and in this case, 0 means equilibrium. All right, let's do an example. Nitrogen dioxide is the substance responsible for the brown haze that is known broadly as smog. In automobile engines, nitrogen and oxygen will react to form nitrogen monoxide, which then combines with more oxygen in the atmosphere to form nitrogen dioxide. What is the value for the standard free energy change at 298 Kelvin if the standard enthalpy of reaction is negative 114.2 kilojoules and the standard entropy of reaction is negative 146.5 joules per Kelvin? So this is a very straightforward application of the Gibbs free energy equation. Delta G is equal to delta H minus T delta S. We are being given the delta H, negative 114.2 kilojoules. We are given the temperature, 298 Kelvin. And we're being given the delta S value, negative 146.5 joules per Kelvin. Now, before we start multiplying stuff together, we do need to recognize that our normal ways of expressing enthalpy and entropy naturally have a unit mismatch. Enthalpies are usually given to us in kilojoules per mole. Entropies are usually given to us in joules per mole Kelvin. So we've got to resolve the unit mismatch before we start multiplying and combining terms. Now, I am on record as normally saying that I like to convert kilojoules to joules usually. There are a couple of exceptions to that rule, and this is one of them. And the reason why this is one of them is because delta G is also usually expressed in kilojoules. And so for that reason, it makes way more sense to convert the entropy to kilojoules than to convert everything to joules, do the calculation, and then convert it back to kilojoules again. So that's the perspective I kind of take on this. And so if we're looking at it from that perspective, if you are being asked to calculate joule or free energy or enthalpy, kilojoules is the way to go. If you're being asked to calculate entropy out of this equation, you're going to have to do a conversion to joules at some point, but you probably can save it till the end. So to solve this mismatch, I'm going to rewrite the first part here, negative 114.2 kilojoules minus 298 Kelvin. We're going to convert this joules to kilojoules. So we need to divide by 1,000. So the decimal point moves over 3 spaces. So it's 0.1465 kilojoules per Kelvin. Now we can start to combine terms. Negative 114.2 kilojoules is still delta H. The product of T and delta S, 298 times negative 0.1465 is negative 43.7 kilojoules. The negative of a negative turns that into a positive. So delta G is equal to negative 70.5 kilojoules. So pretty simple, very straightforward application of that Gibbs free energy calculation equation. Any questions before we move on to the next thing? So like we saw for enthalpy, like we saw for entropy, there are values that we can associate with individual substances at a given phase. For free energy, we call them the free energies of formation. This is very similar to the enthalpies of formation that we saw in thermochemistry. The free energy of formation is the amount of free energy associated with the synthesis of 1 mole of a substance from its component elements. Now that sounds familiar because that's the exact definition we used for enthalpy of formation in chapter 10, which means since we are talking about the formation of a substance from its component elements, if we are talking about an element, the free energy of formation for that element in its standard state is 0. So once again, if we have elements that are in their normal phases, so nitrogen as a gas, oxygen as a gas, phosphorus as a solid, sulfur as a solid, whatever the case may be, so long as they are in their standard state, their free energy of formation will be 0. Now, it can get a little bit tricky if you start looking at some of those non-metallic elements that have multiple allotropes. So for carbon, for example, we want to look for graphite as opposed to diamond. Free energy of formation for carbon as graphite is 0. For diamond, it is 2.90 kilojoules per mole. Those little things do make a difference. And so do phases. Looking at the difference between water in the gas phase versus water in the liquid phase versus water in the solid phase. They would all have different free energies of formation. So we've got to be careful with those phases. But what it allows us to do is, again, a very familiar form of equation here. The free energy of a reaction is equal to the sum of all of the free energies of formation for the products minus all of the free energies of formation for the reactants. Again, this equation should look familiar as well because we did a very similar form of it in chapter 10 with enthalpy of formation. And we did a very similar form of it yesterday with the standard molar entropies. The equations look exactly the same. We're just substituting one thermodynamic factor for another. As an example, let's go ahead and do this reaction here. P4 and chlorine making PCl3. So P4 in the gas phase has a free energy of formation of 24.44 kilojoules per mole. Chlorine is an element in its standard state, so its free energy of formation is 0. Phosphorus trichloride in the gas phase, negative 267.8 kilojoules per mole. So if I was going to set up delta G here, delta G is equal to the products. So that'd be 4 times negative 267.8 kilojoules per mole times the 4 moles. That's all of the products minus the sum of P4, 1 mole, times 24.44 kilojoules per mole, plus 6 times 0 kilojoules per mole. Four times negative 267.8 is negative 1071.2 kilojoules minus 24.44 kilojoules. So delta G would be the sum of those two. So negative 1095.6 kilojoules. So obviously this is a spontaneous process. There's really no doubt about it. Gives off a ton of energy when it reacts. Now, one thing to keep in mind, just to kind of reinforce, just because we have a really high negative value of delta G says nothing about its reaction speed. You got to keep thermodynamics and kinetics separate from each other. A reaction can be really, really fast, but also barely spontaneous according to its delta G value. You also have a great negative delta G and be kinetically glacial in its reaction speed. The two have nothing to do with each other. Right? Any questions with free energies of formation? So with this kind of in mind, we can see that there is a relationship between spontaneity, enthalpy, and entropy. And we made a table similar to this in lab yesterday. If enthalpy is negative and entropy is positive, then we will get a delta G that is always negative, and so we can conclude that it is spontaneous at all temperatures. And if we have the opposite, an endothermic reaction that has a lack of entropy positivity, then delta G is always positive. It will never be spontaneous, regardless of what temperature we use. When these two terms match each other, then we have temperature dependence. And when our reactions are temperature dependent, we can determine what the value will be for that temperature that will ultimately flip it in favor of the reaction or out of favor with the reaction. And the calculation that does that is temperature is equal to delta H over delta S. So when we do that calculation, delta H over delta S, that tells us the temperature at which the reaction suddenly becomes spontaneous if it's non-spontaneous, or non-spontaneous if it is spontaneous. We call that the flipping temperature. That's where the reaction flips from being spontaneous to non-spontaneous, or vice versa. Let's take a look at another example. We have a reaction with the thermodynamic data seen here. Let's evaluate it. Is this an exothermic or an endothermic reaction? Absolutely. I can see delta H here is negative. Negative delta H means that thermal energy is being outputted. That would be an exothermic process. Is disorder being increased or decreased? So remember, entropy, disorder is another way of talking about entropy. We talk about the randomness of the molecules, the diversity of the ways that they can distribute that energy. We can kind of blanket term that as disorder. So is entropy going up or going down? It's definitely going down. We've got a negative value here. So disorder is decreasing in this process. So since both values are negative, we know that we have a temperature dependent situation here. So to figure out and answer this last question, we're going to have to do the calculation. So delta G is equal to delta H minus T delta S, negative 35.4 kilojoules minus 298 Kelvin. And again, we're going to change the joules here to kilojoules since we are calculating delta G. So 85.5 would be negative 0.0855 kilojoules per Kelvin. So now we do the multiplication. 298 times negative 0.0855 is negative 25.5 kilojoules. So delta G is equal to negative 35.4 minus negative 25.5. And that would give us, to one decimal place, negative 9.9 kilojoules. So is the reaction spontaneous at 298 Kelvin? The answer there is yes. Delta G is negative under those conditions. Now, if we were asked a different kind of question, at what temperature does it cease to be spontaneous? That would be where we would do an application of delta H over delta S. So negative 35.4 kilojoules divided by negative 0.0855 kilojoules per Kelvin. And the three significant figures, that would give me 414 Kelvin. So this reaction would be spontaneous all the way up to 414 Kelvin. At 414 Kelvin, it would be at equilibrium. And above 414 Kelvin, it would be non-spontaneous. So that's what that flipping temperature calculation gives us. We know from this table that the reaction is going to be spontaneous at low temperatures. What that table doesn't tell us is that low temperature and high temperature are relative values. What's low for one reaction might be high for another. That's why we have to do this calculation. And what the calculation tells us is that 414 degrees Kelvin, that's our tipping point. 414 Kelvin is roughly 141 degrees Celsius. And so long as we can keep that value under 141 degrees Celsius, the reaction will run as normal or as proper. All right, any questions? All right, let's look at another one. Gas phase reaction between methanol and water that produces carbon dioxide is accompanied by an increase in entropy, 176.9 joules per Kelvin under standard conditions. At what temperatures is this reaction spontaneous? So we've been given a delta S of reaction value, but we have not been given a delta H of reaction value. Where is that going to come from? Well, we're going to have to use the enthalpies of formation to get us there. So delta H of reaction is going to be equal to the heat of formation of carbon dioxide plus 3 times the heat of formation of hydrogen minus the sum of the heat of formation for methanol and the heat of formation for water in the gas phase. So these values you get out of a reference text, either the appendices in your book, a CRC handbook, your lecture packet. You get them from somewhere like that. And which one you use, again, really just depends on what you need to do. So for carbon dioxide, it is negative 393.5. For hydrogen, hydrogen is an element in its standard state, so this is 0. For methanol, CH3OH in the gas phase is negative 201. And water in the gas phase is negative 242. So the heat of reaction is going to be negative 393.5 plus 201 plus 242 positive 49.5 kilojoules. So we have a circumstance here where both the enthalpy and the entropy are positive. Now we can go back to this table and recognize that that means that it's going to be spontaneous at high temperatures and non-spontaneous at low temperatures. But what exactly does high or low mean? That's where we need to do this flipping temperature calculation. So T is equal to delta H over delta S, 49.5 kilojoules divided by 0.1769 kilojoules per Kelvin. To 3 significant figures, this would be 280 Kelvin. So the flipping temperature is 280 Kelvin. Again, our interpretation here is this is a reaction that is going to be spontaneous at higher temperatures rather than lower temperatures. So when is it spontaneous? It's spontaneous when T is greater than 280 Kelvin. So 280 Kelvin represents the equilibrium point. Anything above it would be spontaneous in this case. Anything below it would be non-spontaneous. All right, any questions with this one? All right, go ahead and try this one out then. You got a reaction where delta H is negative 32 kilojoules and delta S is negative 98 joules per Kelvin. What would the value of T be when delta G is equal to 0? So go ahead and set this one up, see what you come up with, and we'll come back and look at it in just a minute here. All right, let's see how we did. So the information that we need is on this slide. Delta H was negative 32 kilojoules. Delta S was negative 98. What we want is, what is the temperature at delta G is equal to 0? Now, this is a dressed up way of saying what is the flipping temperature, because the flipping temperature records the equilibrium point, delta G is equal to 0. That's actually where that equation comes from. So, I mean, you can set it up. 0 is equal to negative 32 kilojoules minus T negative 0.098 kilojoules per Kelvin. You could do all of that work. And if you did the algebra, you'd end up with T times 0.098 kilojoules per Kelvin is equal to negative 32 kilojoules. And then T would be equal to negative 32 kilojoules over negative 0.098 kilojoules per Kelvin. Rounding to two significant figures, you get 330 Kelvin as the answer. So even if you didn't recognize that this question was just asking us for a flipping temperature, you could have gone through the Gibbs free energy equation and plugged in the 0, the negative 32, and the negative 98 converted to kilojoules, and got to the exact same place without it. And that's kind of an important takeaway for this question, really, is that if you don't remember the flipping temperature, remember that you can always solve for when delta G is equal to 0. And you'll get to the same place. Because that's the difference between spontaneous and non-spontaneous, right? If spontaneous is negative and non-spontaneous is positive, then the spot in the middle is the thing between negative and positive, which would be 0. All right, any questions with this example? All right, let's go ahead and try another. Now for this, you're going to need some sort of reference. So either pull out the appendix tables that I've given to you electronically, or find the values in the appendix in your textbook, whatever you need to do, but you're going to find the free energy of this reaction using the free energies of formation. So chew on that one for a couple of minutes and we'll come back and see how you did. And we'll go ahead and take our break for this morning as well. All right, let's see how we did. So the real key to this question was we had to find the free energies of formation. Now the lecture packet had them in there. You probably should be able to find them in the appendices as well. Depending on your source, you're going to find slightly different values, but we had to make sure that we got the correct ones. So that meant that for the ethanol, we had to grab the formation value for the liquid form, not the gas form. There's about a 6 kilojoule energy difference there. And the same thing for the water. We had to make sure that we got the correct value there as well, because the difference between the two is about an 8 kilojoule difference there as well. Just enough to kind of set things off a little bit. So to find delta G, it's the sum of the products minus the sum of the reactants. So we have 2 times negative 394 kilojoules plus 3 times negative 237 kilojoules minus negative 175 kilojoules and 3 times 0. So just the negative 175. So 2 times negative 394 plus 3 times negative 237 plus 175 gives us a grand total of negative 1,324 kilojoules. All right, any questions with this example? All right, let's stop here and take a short break. Come back and we'll finish out the chapter and have some time to review.